Good morning, viewers. Let us discuss an interesting topic coming under physical chemistry, that of solid state, namely structure of simple ionic compound. As you know, solids contain the constituent particles which are closely packed. Solids are of two types, crystalline and amorphous. In crystalline solids, the constituent particles are arranged in a regular repeating geometric pattern, whereas that is absent in amorphous. Now, based on the kind of constituent particles present, crystalline solids are again of four types, that is covalent crystals, ionic, metallic, and molecular solids. Now, our discussion will be restricted to only this type, ionic solids. Now, you know that any ionic solid contain positive and negative ions, what we call cations and anions, of which anion is generally bigger in size than the cations. So the cations are found to enter the void, the empty space present in the close packing of anions. That way we can explain the crystalline structure of ionic solids. So to explain this, to understand this concept, we need to look closely at what are voids. In any close packing, you can see mainly two types of voids. The empty space present in crystals, which are properly called interstitial voids or interstitial sites, mainly of two types. One is tetrahedral void and the other is octahedral void. A tetrahedral void is the empty space at the center of four touching spheres. In a close packing, you can see this kind of assembly, four spheres are touching, and you can see an empty space inside. So if you take a smaller ball which is small enough to be kept inside, that can be kept inside the hole. If you join the centers of all the four spheres, you get a regular tetrahedron. That's why the name tetrahedral void. Now, you can have a bigger kind of void with six spheres which are kept in an inverted fashion, that is the spheres in two layers, which make up a bigger empty space inside. You can see where you can keep a little bigger ball compared to what you keep in a tetrahedral void. So this is a little bigger void, and apart from these two common type of void, there is also another type of void called cubic void, which is still bigger in size. To understand that, you think of these 4 balls which are touching, and you have another 4 balls which are kept just above this 4 ball in touching. So you have an empty space inside which is still bigger. So altogether you have 4 types of voids. Tetrahedral void can be shown like this, 3 spheres touching in one layer, and you have one sphere above it kept in the depression. So you will have a small empty space inside this. Remember, we have an assumption here. In any kind of crystals, the concerned particle, whether it is atom, ion or molecule, we assume it to be spherical. So we consider the packing of spheres as the packing of concerned particles. Now, in octahedral void is formed by 6 spheres in touching each other, 3 in one layer, and the next 3 in the second layer, which will be coming in inverted fashion. It's clear that this is a little more open structure, so that the empty space inside will be bigger than in this. And in the case of a cubic void, which is the largest one, you have 8 spheres touching each other, and you have a much bigger empty space. So these are the spheres, one in the first layer, and you have in the second layer another 4. So inside this assembly there will be an empty space which is bigger than this. This octahedral void is called so because if you join the center of the 6 spheres, you will be getting a regular octahedron. And this is obviously a void inside a cube. Now, to compare the size of these voids, it is a normal practice to write a ratio of the radius of void to the radius of the sphere. In the case of tetrahedral void, it is mathematically you can easily derive this, work out this value, which is 0.225 in the case of a tetrahedral void, which increases to 0.414 in the case of octahedral void, and it is 0.732 in the case of cubic void. So obviously, the size of the void is increasing. Now, in the case of ionic solids, when we discuss the structure of ionic solids, as I told you earlier, it is the cation which is generally smaller inside, which could enter the void, and anions make up the close packing. Again, to locate the voids, particularly the tetrahedral and octahedral void in a CCP unit cell, this is the unit cell of cubic close packing, which is also equivalent to what is called FCC or face-centered cubic lattice. Here, this is an FCC or CCP arrangement, the unit cell. You can see that this is FCC because there are 8 particles in the corners. This is the corner of the cube, and there are 1 particle in the face center. You have 6 faces for a cube. So these are the particles. Now, the voids, the tetrahedral void in this unit cell is actually, as we have seen earlier, 4 touching spheres. You can see 1, 2, 3 and 4. So this corner particle has a tetrahedral void just behind this, that is here. So behind every corner particle there is a tetrahedral void which is well inside this unit cell. So there are altogether 8 corners. So there are 8 tetrahedral voids in the unit cell of CCP or FCC. Remember, the effective number of particles for an FCC or CCP unit cell is 4 because Each corner is shared among 8 unit cells, and the face center is face centered particle is shared between 2 unit cell. One is this and one is the above this. So if you calculate 1 by 8 into 8 corners plus 1 by 2 into 6, it is 4. So effectively in this unit cell there are only 4 particles, and you can see there are 8 tetrahedral voids. Now what about the octahedral void? You can see these particles, that is 1, 2, 3, 4, that's the face centered particle, and one above this and one below this. That means all the face centered particle, if you cut them out, you can see inside that there is a octahedral void. So that is actually the exact center of this cube. It's an octahedral void fully inside the unit cell. In addition, all these edge centers are the part of octahedral voids which are shared with other unit cell. You know, an edge of a cube is cubic unit cell is shared among 4 unit cells, so it's a share of 1 by 4. 1 by 4 into 12 edges are there for a cube. So 1 by 4 into 12, it is 3, plus 1 fully inside, it is 4. So we come to the conclusion that in the unit cell of CCP or FCC, there are 8 in a CCP or FCC unit cell. There are 8 tetrahedral voids, and there are 4 octahedral voids. Right? Now, keeping this in mind, we can now explain various structures of various simple ionic solids of AB and AB2 type. Again, before entering to that, you can see this is again an unit cell, an FCC unit cell. You may, for the time being, forget about this gray board. Consider only the green boards. Hello, and there's no gray board, suppose. So the arrangement is of the green ball is again FCC. You have 1, 2, these are the corners. You have 8 corners. You have the particle, and at the face center you have the particle. Then what's the difference between the two? This is called space filling model, where we show the particle in its real size so that they touch each other. Whereas this kind of structure is to appreciate the cubic shape of the molecule, the geometry. It is cubic, and we show the particles only as points, as lattice points. Actually, these particles are bigger such that they touch each other. Here also, as we have seen here, let us just recap the location of tetrahedral or octahedral voids in the unit cell. As I told you earlier, behind each corner particle there is a tetrahedral void. So somewhere here is a tetrahedral void. If you are increasing the size of these 4 spheres, they will be touching and there will be a small empty space inside. And you can appreciate this again if you join these 4 green balls. Definitely you can see a tetrahedron, and the center is the void. So like that, behind each corner particle there is a tetrahedral void. So this big cube has 8 smaller cubes. At the center of each smaller cube, it's a tetrahedral void. Now what about octahedral void? As I told you in the space filling model, the exact center of the cube is an octahedral void, that is this point. Because if you join the face center particle like 1, 2, 3, 4, connect these two, and then one above and one below, join all of them, you get an octahedron, isn't it? And the center is the empty space, which is an octahedral void. The edge center is a part of it, it is shared among other unit cells. So this you have 12 edges. All these edge centers are also octahedral void. Now let us come to the discussion of various ionic solids, considering AB and AB2 type of solids. As I told you earlier again, the cations are occupying the voids which produced by the close packing of anions. Then comes the question, which void will be occupied, whether it is tetrahedral void, octahedral void or cubic void, which are different in size. So that is decided by what is known as radius ratio, that is R plus by R minus. Radius of cation by radius of anion, which is similar to radius of void by radius of sphere. Remember, anions are the big particle which make up the close packing. So that's in place of the spheres, and the void, the small empty space, is occupied by the cation. So this ratio, radius of cation by radius of anion, is known as radius ratio. That will decide which void will be occupied by the cations. So we have a limiting radius ratio values. Limiting radius ratio, like the typical value of tetrahedral void is 0.225 up to 0.414, that is that of octahedral void. In this range, the coordination number will be 4. The geometry type, if it is 4 means, this is the tetrahedral void, so the void will be at the center of 4 spheres, so this is tetrahedral geometry. That means the 4 anions make up the close packing, and in the void there is a tetrahedral void cation will be placed. Let us put example for this: zinc sulfide, beryllium sulfide, etc. belong to this category. Then the next range is 414 to 0.732. Then it is the octahedral occupancy. So the coordination number, as you know, is the number of particles immediately around each particle in the crystal lattice. It is then octahedral geometry. Example is sodium chloride is an example, and you can also put another example. There is magnesium oxide. Then many more are there, and the last one is 0.7321. A very big anion has to occupy octahedral void. So if you keep a cation inside an a cubic void, it will have 8 neighbors around. So that is known as cubic occupancy. Example for this is cesium chloride, calcium fluoride. Okay, let us now look into these structures. Starting with the first one, that is zinc sulfide structure, which is called zinc blende structure, or also called sphalerite. So in this case, if you take the ratio of radius of zinc ion to that of sulfide ion, it is found to be 0.4. That's the value, radius ratio. So this comes in this range. That means here the zinc ion can go into the tetrahedral void. So what is the kind of arrangement? In the case of zinc sulfide, sulfide ion make up the close packing, that is CCP, and zinc ion enter the half of the tetrahedral void. So that is related to the stoichiometry of the compound. So as we have seen earlier, CCP means effective number of particles will be 4. So there are 4 sulfide ions in the unit cell. And we know in the unit cell there are 8 tetrahedral void, so you have to have only 4 zinc ions. So that's why half of the tetrahedral void, that means it will be half of 8, that is 4 zinc ions. So in the unit cell of zinc sulfide there are 4 sulfide ions and 4 zinc ions, so it is altogether 4 zinc sulfide units are present in the unit cell of zinc sulfide, that is sphalerite. Now the coordination number, we know zinc ion is in the tetrahedral void, so the coordination number of zinc ion is 4, and you can see that of sulfide is also 4. So the coordination number of this arrangement is 4:4. We can make this more clear with the model. Consider these are the sulfide ions which make up the CCP or FCC arrangement. So zinc ions will go into the tetrahedral void, only half of it. So we know that behind the corner particles there is tetrahedral void, there are such 8. So zinc ions will go into alternate tetrahedral void. If it goes to this one, there is no zinc ion here. This will be occupied, this not, and below it will be just opposite. This can be understood from this model also. If you again consider on the green balls in place of sulfide ion, and you forget about the gray ball, there is no gray ball here. So considering only the green balls, it is an FCC arrangement. Behind the corner particle there will be a tetrahedral void. So zinc ion will be over here, and not here, it will be here, and there is no zinc ion here. So these two places are occupied, and here it will be these two. So if you join these 4 zinc ions, if you join them, you get again a tetrahedron. So here, if you have a zinc ion here, or if you have a zinc ion here, it is in the middle of these 4 sulfide ions. So both way, it is the coordination is 4:4. We can go into the next one, that is the octahedral geometry in the case of sodium chloride. In sodium chloride, if you look into the radius ratio of Na plus to that of Cl minus, it is a little bigger. It is 0.54. So you cannot keep a sodium ion inside a tetrahedral void, is bigger. So you have to go into the second range, that is that of octahedral occupancy. So sodium chloride will have an arrangement in this way. Chloride ion, which are the bigger one, make up the FCC array. So there will be, it will result in 4 Cl minus ions in the unit cell, and Na plus go to all the octahedral voids. All the octahedral voids, because as we have seen earlier, an FCC unit cell has got 4 octahedral voids, so that will be occupied by Na plus. So altogether, per unit cell, sodium chloride has got 4 NaCl units. And the coordination, since Na plus is in the octahedral void, definitely around sodium there are 6 chloride ions, and vice versa. You can definitely see that there are 6 sodium ions around each chloride ion. Now this model is exactly that of NaCl. These green balls represent the chloride ions, which are in FCC arrangement, 8 corners and the face center, and the grey ball here stands for sodium ion at the 12 edge center and 1 at the body center. This is the octahedral void which we have seen earlier. So you can see that sodium chloride contain per unit cell there are 4 NaCl units. Now let us take the last one, that is cubic type of coordination. example is cesium chloride. Compared to chloride, cesium is not that small, it is almost the size of chloride. So the radius ratio is much larger. Radius of cesium to that of chloride is something nearly 0.9, nearly 1. It is 0.943. So cesium is roughly as big as chloride. So cesium cannot go into tetrahedral or octahedral void. So the structure will be now a cubic occupancy. That means chloride make up a cubic void and cesium enter into it. So the structure can be explained in a very simple way. You have a primitive cubic, that's the cubic arrangement of chloride ion. Simple cubic arrangement or primitive cubic. So there are chloride ions only at the corners. So that will amount to 1 chloride ion because each corner has 1/8 contribution. So effective number is 1, and you have an cubic void inside that is occupied by cesium ion. So there is 1 cesium also. So per unit cell, in the case of cesium chloride, there is only 1 cesium chloride unit. The coordination, since cesium ion is in the cubic void, it is in the cubic void, definitely its coordination is 8, and naturally you will see that chloride ion is also having a coordination 8. So a coordination number is increasing. So in the discussion we have seen, as the radius ratio increases, means the size of the void increases, coordination number increases. This is known as radius ratio rule. So these are various simple ionic solids of AB type, in which we can explain their coordination, their geometry by considering their radius ratio. And one more example is the one which again has the cubic occupancy, that is calcium fluoride. You can see it's an AB2 type, the stoichiometry is 1:2. Here, this one also comes in this category because the radius of fluoride to that of calcium is coming in this range. So here, fluoride make up the simple cubic or cubic arrangement, primitive cubic arrangement, and the calcium ion goes to half of the cubic voids. So to explain this one, you need a bigger unit cell. I will explain this model. Look, here now you have to have an assumption that this gray ball is also green. So all balls are green. And if you take this small cube from this, that's the unit cell of this big one. All the balls are green. So consider this green ball as fluoride ion. So fluoride ion is having a primitive cubic arrangement, simple cubic. So this is a cubic void, right? So considering all these fluoride ion in this big unit cell, the total number of fluoride ion will be equal to 8. If you consider this, if you consider only this small cube, it is simple cubic, so 1/8 into 8, so it's only one particle. So there are such 8 cubes, so the total number of fluoride is 8, so 8F minus. So for 8F minus, stoichiometrically you need only 4 calcium ion to balance the charge and the stoichiometry. So only 4 calcium can be kept in the voids. So you have 8 cubic voids at the center of each of these cubes. So all the cubic void cannot be occupied. So you will have this cubic void occupied by calcium ion. This will be empty. Calcium will be here, not here. And here it will be just opposite. Calcium here and here. as in the case of zinc sulfide. So half of the octahedral void is occupied, half of the cubic void occupied. So it will be just 4. So 4 calcium 2 plus. See, so 4 calcium 2 plus and 8 minus, it will amount 4 calcium fluoride units in the unit cell. So the unit cell of calcium fluoride is explained with this big model. Whereas in the case of cesium chloride, you can explain the unit cell with this small cube only. If you consider this small cube and all the corners are occupied by chloride ions, consider these gray balls are also green. So primitive cubic arrangement of chloride ion, and you have cesium ion at the center. So it is one chloride and one cesium. So that will completely explain the stoichiometry of cesium chloride. So these are the various types of simple ionic solids of AB and AB2 type, whose structure can be easily explained with these models. You can have a look at these videos which will again support your learning. That of zinc sulfide, look at this. See how the packing of the array of unit cell takes place. Look at each unit cell. In zinc sulfide you can see FCC arrangement of sulfide, and that's a green ball, and zinc ions you can see in the tetrahedral void only alternate tetrahedral void. In one unit cell there are 4 zinc ions. So that is the joining of 2 unit cell and more coming. You know, a crystal is made up of so many unit cell put together. So that is how a complete crystal of zinc sulfide is developed with a number of such unit cells. If you check the coordination number of any particle, you can see it is 4:4. Now let us see. I think it is enough to understand the concept. Let us go to the next higher coordination, that of sodium chloride, where the occupancy is octahedral void. One thing to be made clear is, here the arrangement, this unit cell is shown like the green balls, that is the bigger chloride, is kept in the octahedral void, and the sodium and the pink one is kept in the FCC pattern. So that's the beauty of crystalline structure. You can explain the structure of NaCl in both ways. Like chloride ion make up the FCC pattern and Na plus enter the void, or vice versa. Actually, it is that there are 2 lattices, FCC lattice, one that of Na plus and the other that of Cl minus, which are interpenetrated halfway. So that is the actual arrangement of sodium and chloride ions in NaCl. So the pattern is repeated all around, you can see that coordination number is maintained. There is 6:6 everywhere. So this is how this unit cell, the crystal of sodium chloride, is developed. So this can be shown the other way around, the other also, that you keep the green balls in the FCC pattern of the unit cell and keep sodium ion in the octahedral void. Doesn't make any difference. When you make up a whole crystal, it will be the same. Okay, another thing to be mentioned here is that in the octahedral void ratio is actually 0.414, that's the typical value, the ideal value, whereas the radius ratio of sodium chloride is actually 0.54. That means it is more than the ideal ratio. So how the sodium ions occupy the void is that the chloride ions will slightly open up and make the void a little bigger than the ideal size, so that sodium ion can enter. So that's the case of almost all ionic solids. It will not be a perfect fit, a perfect close packing. Finally, let us see that of cesium chloride. It's a cubic coordination. Cesium ion occupying the empty space of chloride ion. You may see it is shown the other way around. Cesium ion at the corners and chloride at the center. Doesn't make any difference once the crystal is developed. So it is the simple cubic arrangement of one ion and the other one entering the octahedral void. So a number of unit cells of cesium chloride is joining to make up the whole crystal. So you can see that now the chloride ions, the green big ones, are 8. If you join that, you get a cube, and at the center you can see the sodium ion. So both way it is correct. That is, cesium ion enter the void or chloride ion enter the void of the close packing of the other ion. Right. Now it is up to you that you make such models using balls and glues. You can make any kind of structures, and you can use small beads or smaller balls and keep in the voids and develop such models. And then this learning the structure of ionic solid will be an interesting one. Thank you.